All right, with that, we'll get back into chapter 2 this morning. So last week we started our discussion on chapter 2. If you recall, it's on atoms, molecules, ions. We'll get into some nomenclature conventions at the end of the chapter. Might even start naming some things towards the end of today's lecture. But at the end of lecture on Friday, we were talking about those fundamental experiments that went into determining that the atom is divisible. So we found that you could eject an electron from an atom by subjecting a stream of atoms to a high voltage of electricity. So a high amount of electricity kicks an electron off, a negative particle. We then found through the Millikan oil drop experiment that the electron's very, very small, not much mass, very low mass, much less mass than the lightest known element. So the mass of the electron is about 1/500th the mass of hydrogen, which is the lightest element. Now, at this time, we were still trying to discover what it was that made elements different from each other. We still hadn't quite determined that it was, or maybe around this time, we're also determining that the number of protons in the nucleus is what's changing the properties of an atom or an element from one element to the other. But we'll get into that later today of what makes the elements different from each other. We then also saw a radioactivity set of experiments from Curie, where 3 radioactive pathways were found, the alpha, beta, gamma ray. I don't know if it's worth remembering which one's which, but the beta is the electron. So we can see some elements that are radioactively decaying are just giving off an electron as they decay. Other forms of decay, one of them was the gamma ray. That's just like a high energy packet of light, kind of like an X-ray, but even higher in energy. And then there's the alpha particle. The alpha particle, we said, was the helium nuclei, which turns out to be one of the most stable, if not the most stable nucleus. So a lot of elements, especially on the bigger side, we're talking about how some of the elements beyond uranium have already decayed into smaller elements. One of those main decay pathways is for an element to lose the equivalent of a helium nuclei off of its nucleus and then have whatever's left over. Radioactive pathways are taught as a topic more in chapter 23 later in the textbook. You might see those in 1220. So we're just trying to roughly introduce the concept that some elements are radioactively decaying through a couple of key different pathways or through a key different number of particles that are given off the alpha, beta, gamma ray. But then we saw the alpha particle was scattered by atoms, and so that was the Rutherford gold foil experiment. And the scattering was due to these compact nuclei. So it led to the sort of idea that whenever one of those alpha particles struck a nucleus of the gold atom, it was deflected off the atom. If not for the compact nucleus with a large amount of mass, then the particle likely would not have been ever scattered and would have went right through that gold foil. So it was the scattering of that alpha particle that let us discover the nucleus of the atom and put that forth as the model that we have going forward. So this is from Rutherford's postulate from his experiments. So most of the atom is the empty space that's occupied by those very light electrons. The electrons are spinning around the nucleus. We'll talk about orbitals and configurations in chapter 6. You may have learned that previously. So most of the atom is actually the space that's occupied by those very light electrons as they're spinning around the nucleus that contains most of the mass. The size of atoms is very small, about 1 to 5 angstrom in diameter. So that turns out to be 100 to 500 picometers. That's 100 to 500 times 10 to the minus 12 meters. So really small in terms of the size of our atom. 1 angstrom is a 10 to the minus 10 meter. So you can also say it's about 1 to 5 times 10 to the minus 10 meters in terms of the size. There's a lot of examples you could do to portray how small an atom is. One of those is like if you had a pencil, like if you imagine a graphite pencil and graphite is really carbon atoms. So graphite pencil, or what we call a lead pencil, is really graphite. And so graphite's carbon, or a form of carbon. If you had carbon atoms aligned in this sort of fashion here, end on end across that one little stroke of a pencil, that you could get about 1 million carbon atoms aligned end on end across, a just small little strip of a pencil stroke. So the atom, of course, is very, very small. We'll see also when we get to Avogadro's number that when we start looking at how many atoms there are within a quantity we call the mole, we'll see also that the atom, of course, is very, very small. And so our subatomic particles, protons, nucleus, reside in the nucleus, and then the electrons outside of the nucleus. So the nucleus are where those more massive particles are found. So this also is looking at the relative mass of the proton, neutron, and the electron. And so the proton and neutron, slightly different masses, but around 1 atomic mass unit. We'll define and talk more about the atomic mass unit scale as we go on, but the atomic mass unit scale is just a way of sort of portraying or defining the mass of these really small particles. We'll see in a moment, maybe even later today, that a carbon-12 nucleus, we'll have to define a little bit more to kind of know what we really mean by carbon-12, but we'll get into what we mean by the symbol. But this mass of one single atom of carbon-12 is defined to be precisely 12 atomic mass units. Just to give you a sense that the atomic mass unit is really, really small. It's defined, so 12 of these atomic mass units on this atomic mass unit scale is the mass of a single carbon-12 atom. Again, we'll talk more about the AMU scale, but I just wanted to give you a sense of just how small that mass scale is corresponding to. So the single atom has this mass of 12 AMU. So about 1/12 the mass of carbon is due to each of the protons it would contain, and then 1/12 of the mass of carbon is due to the neutrons it contains. It turns out carbon-12, we could also write this number 6 down here. Let's define a few of these numbers here, because we do want to talk about atomic symbols, mass numbers, and isotopes as we get into this discussion here in chapter 2. The atomic number is the one down below. The atomic number is the sort of number that defines the atom, and then that defines the number of protons in the nucleus of that atom. So the atomic number tells us the number of protons within the nucleus of that atom. So if we go to our periodic table, hydrogen has 1 proton in its nucleus because it's element number 1. Element number 2 is helium, so it has 2 protons in its nucleus. Lithium 3, beryllium 4, boron 5, carbon 6. So carbon is the 6th element, therefore it's defined as the element that has 6 protons within its nucleus. If we continue, if we just look at any random element like argon, number 18, has 18 protons in its nucleus. So when you get a periodic table, you'll always get the sort of symbol on the table, you'll get that atomic number. So you'll always get to see the atomic number. Even if you go very big, uranium, U92. So very simple, uranium would have 92 protons within its nucleus. And so that's what makes elements different from each other, is that positive particle, the proton. So notice that the proton has a +1 charge. And then the proton's charge is just the opposite of the electron. If you recall, the electron's charge was found in that Millikan experiment. You don't have to have this memorized, but it was negative 1.6 times 10 to the minus 19 coulombs is the actual electrical charge. And so the proton's charge would be plus 1.6 times 10 to the minus 19 coulombs. Just to give you the sense that whatever the charge of the electron is negative, the proton's that same charge positive. But then massively different masses. So notice that that electron very, very light compared to the mass of the proton or the neutron. Now let's get at the neutron discussion. Where does that come into play? Well, it comes into play through part of this number here up top, which is our mass number. The mass number is the sum of the number of protons plus the number of neutrons in the nucleus of that atom, because those are the 2 particles that carry most of the mass of the atom. And so we call the mass number the sum of those 2 particles, the protons and the neutrons, that carry the majority of the mass. We're not summing the electrons into the mass number because they carry such a small amount of mass that we don't include them into the mass number. And so if we know carbon has 6 protons and it has a mass number of 12, then carbon-12 would contain 6 neutrons. Now, you can look at the periodic table and get the proton count just based on the atomic number, but you can't just look at the periodic table and guess the number of neutrons that an element would contain. And also, most elements can contain more than one set of neutrons in a nucleus that could be stable. For example, carbon exists as carbon-12. It can also exist as carbon-13. If you look at a natural sample of carbon, it's mostly carbon-12, about 99% carbon-12. About 1% or so is carbon-13. And carbon-13's difference from carbon-12 is that 1 extra neutral particle. So this carbon-13 would have 7 neutrons and still, of course, 6 protons. So we're not changing the proton count is locked in by the element. So if we look at carbon-13, the proton count isn't different, it's the neutron count that's different. Carbon-14 also is a carbon atom that is found in natural samples. It's only present in very, very trace quantities. It's like less than 10 to the minus 10% of a natural sample. It's such a small amount of carbon, but any sample that contains carbon, like such as our bodies or an artifact or something that you find in nature, that those items have such a large amount of carbon that you can usually spot these carbon-14s. And there's experiments that can detect the amount of carbon-14, and you can actually date objects by how much carbon-14 they contain, because carbon-14 is not a natural occurring isotope. Carbon-14 forms from nitrogen decaying, an unstable isotope of nitrogen decaying to form that carbon-14 isotope, and it has a lifetime. This isn't anything you'll be tested on, but the carbon-14 lifetime is about 6,000 years is its half-life, so you can date an object up to about 12,000 years in terms of how old it is based on how much carbon-14 it still has left within it. Again, that's more of a topic for chapter 23 that you might see later, but I just wanted to kind of mention there's some practical applications you could look at for, that the sort of sea of isotopes that you see for a given element could always be in flux based on radioactive pathways that are taking place that are leading to their formation or destruction. So carbon-14 is an unstable nucleus. It's important to recognize maybe it's one of the natural occurring isotopes of carbon, but very, very small trace of carbon. Okay, so we have our mass number up top. That's the superscript before the element. The atomic number comes below. And then the atomic number, we often won't write the atomic number because it's sort of redundant information. So you'll see a lot of times we might write things like 35 Cl, and we won't always write in the number below because we could always look that up on the periodic table. So you can always access the periodic table to see that it's element number 17. So you might see that we'll say, if we need to tell you what isotope of chlorine that you're working with or is important for a problem, we might say 35 chlorine, and then you'll know, if you need to know the proton count, you can check your periodic table. And if you want to know, okay, that's the 17th element, so that's how I know to write in 17, or to understand that chlorine would have 17 protons, and therefore the difference from 35, that would be 18 neutrons. So 18 plus 17 is 35. Now again, I wouldn't expect you to predict the number of neutrons that an element contains. You have to know something, you have to be told information to know the number of neutrons that are present within a given isotope. So we call like carbon 12, 13, 14 are isotopes of each other, the same elements, just with different numbers of neutrons. And then if you're also thinking about properties of an atom, changing the neutron doesn't really change the properties by very much. It just changes the mass of the nucleus slightly. You're not changing the positive particle count or the negative particle count by changing isotopes. So most of the properties of a given element are a balance of how much charge it has in its nucleus versus how many electrons it has near it versus how many electrons it wants to have near it. So we'll get into the discussion that like metals will tend to want to lose electrons to go to a positive charge. Non-metals tend to want to gain electrons to go to a negative charge. We can form ionic compounds. So we may have seen examples like sodium plus Cl minus, where sodium lost an electron to go to plus, chlorine gained an electron to go to minus, and then you have this electrostatic attractive force between the plus and the minus charge it forms. That's what is present within ionic compounds. You then also have the sharing of electrons within like the bonds of H and O and water, or between, say, carbon and hydrogen. So we also can imagine we can have shared electron bonding. So the reason why an atom like carbon would want to share electrons with something like hydrogen, whereas something like sodium and chlorine will donate and accept electrons and form ions, has all to do with the different properties of the elements and their different degrees of how much charge they have. Like carbon is right in the middle of the periodic table, so it's really hard for it to go to like a big plus charge or big minus charge, so it shares its electrons and forms a more stable arrangement of electrons through sharing electrons and covalent bonding. We'll talk a lot about the differences of, and we'll start in this chapter later, talking more about the differences of ionic versus molecular compounds, and then we'll continue that discussion throughout chapters 8 and 9 when we get into bonding and structure and what molecules look like. And then you'll continue that if you take OChem in terms of organic molecules, what they look like, what's important reactions and considerations for those types of molecules. Okay, so I think I hit everything on this slide. So protons, neutrons reside in the nucleus. The protons define the element. It's that positive particle count that defines the element. Electrons, protons, identical. in charge, but opposite in sign, so the charge magnitudes are the same. One last thing I guess I didn't highlight is that if you had a neutral atom, like let's say a neutral atom of carbon, that all these atoms here for carbon would all have 6 electrons to balance out that 6 protons. So if you have a charge neutral atom, the number of electrons has to equal the number of protons. When we're thinking like sodium plus, we had to have lost 1 electron to have that net positive charge. So if we look at sodium, it's element number 11. And so from being element number 11, we know it has 11 protons. And so if we have to have a net positive charge, we're going to lose an electron. So when we create ions, we're kicking electrons on or off the atom. And so to go to a positive charge, we have to have 10 electrons. So 11 positive particles minus our 10 negative particles equals a +1 charge. And so it's that counterbalance of protons and electrons. So if we lose electrons, we end up with a net positive charge on our atom. And then if we gain electrons, so chlorine, element number 17, so 17 positive particles. So if it goes to a negative charge, it's picked up 1 extra electron, and it now has 18 electrons. There's another slide later, or a couple slides later, on counting protons versus electrons, but since I was putting some ions on this chart here, we can think of their imbalance now of protons versus electrons, but it's not the proton count that changes. Protons are in the nucleus of the atom. You're not kicking a proton off an element unless you zap it with like some crazy particles with really high energies, or you bombard atoms at very high velocities together. You're not just like plucking a neutron or a proton off an atom just to change its properties, but you can kick an electron off. It's very small, light on the outside of the atom, so we can exchange electrons much more easily. Okay, so how many protons, neutrons, electrons do these atoms contain? Kind of already did some of these examples here, but we already did the chlorine 35 example on the previous page. 17 protons, we got the 18 neutrons from that difference. And then just to highlight the electron count, if you're looking at an atom that doesn't have a defined charge, if you don't see a plus or a +2 or a minus or a -2, then you're assuming it's charge neutral. So therefore, we have to have 17 electrons. So if the charge is neutral, or if no charge is indicated, we're assuming the charge is 0. Therefore, we have to have an equal number of protons and electrons within the atom. And so then can we write the name and like the atomic symbol for the element that would have the atomic number 26 with the mass number of 56? And so that's iron, Fe. So Fe, iron, has the atomic number 26. So that's our 26 protons. Our mass number was 56 that we're told here for that atom. We take the difference from our sum of our protons and neutrons minus the number of protons. That gives us 30. So we have 30 neutrons. And then 26 electrons to go charge neutral. So we're told atom. So an atom's charge neutral. An ion would be something that would have a charge. If we're told that we had a +3 ion of iron, so if we said you have this with a +3 charge, then you can say, okay, we have 26 protons, and therefore, how many electrons have we lost to go to a net charge of +3? We lost 3 electrons, so we would have 23 electrons. We can write an equation that the charge is just the number of protons minus the number of electrons. We might forget this equation. If we do, I think we just come back to the idea that, well, if iron has 26 pluses and a net +3, we had to have lost 3 minuses. The only thing we can exchange to make ions are electrons, so to get a net positive, we have to have fewer electrons than the protons. So again, counting electrons, again, we've already done some of these examples, but just to highlight that again, or if we forget the example, that for chlorine, it's just looking up 17th element, net negative, we have to pick up 1 extra electron, so 17 protons, 18 electrons. And again, if you think of the charge minus 1 being equal to the number of protons minus the number of electrons, so then I think that math checks out. So if we add 1 to both sides and add the electrons to both sides, and we get the number of electrons is equal to 18. So you can think equation form to get 18 electrons, or you can just think schematically, 17 protons, to get to a net negative, just 1 extra electron. Iron 3 plus, which I picked a different example from the previous page, which is to highlight, and maybe let's change iron to something different. Let's do zinc 2 plus. So zinc, it's almost as easy as the example we already did, because it's just looking up the element number to get our proton count. And then if we lost 2 electrons, then we would pick up the +2 charge, so we'd have 28 electrons. And again, iron was 26, we lost 3 for 23. That's the one we did on the previous page. So I just changed that example. We can go big. Lead is all the way element number 82. So element number 82. So 82 protons, 80 electrons. So I think it's pretty easy to remember. It's that light particle that's spinning around the nucleus. That's the particle easier to kick off an atom to make a cation, a positively charged particle. So we call the positive particles cations. And then the negative particles anions. So we're creating cations by kicking electrons off the atom, and then adding electrons to an atom to create an anion. Let's do a sig fig problem just to kind of take a break. Let me just quickly introduce the problem. Assume that the numbers here are numbers subject to, that they're inexact quantities or subject to sig fig rules, and try to do this calculation. So take a minute or two. You can talk with your neighbors. Okay, let me take a quick poll. How many think, probably nobody thinks it's A. Anybody think it's A? Probably not. Anybody think it's B? Anybody think it's B? Be brave if you think it's B. Anybody think it's C? C, anybody? D? Okay, good. So I think the answer is D. 53 is a weird choice. Anybody think it's 53? Sig figs? Probably not. Okay, so how does this problem work? Well, let's do this step first by sig fig rules, because when we multiply two numbers, we have to do that multiplication before we do the subtraction. So we apply the multiplication rule when we multiply. We're going to multiply first. I get 0.7375 is that multiplication result. And then that would have two significant figures. Now, we could either round here and then do the next step, or just keep the number as it is and then round accordingly when we do the subtraction step. So that's the tricky part sometimes to understand is, well, why or why shouldn't I round? Well, generally speaking, you would like to round just once in a problem. So if you can imagine just doing the math, hitting enter on your calculator, and then trying to figure out how many sig figs you write, and then going back to the question of identify the sig figs here first, and then so we go to the threes placeholder. We don't necessarily round, but we just note in our head that that's the last sig fig in the subtraction step. And then that's the greater quantity placeholder, because I look at the placeholders when I round, when I subtract and add. So I'm going to round to the hundredths placeholder instead of the thousandths placeholder of the 7 value. So the greater value placeholder is the one that 3 ends in. And again, we could round and then do the subtraction and get the right answer, or we could leave it as it is and just note the placeholder that sig fig ends in, or that value ends in, and then do the math. If you're confused by when to round or not round, just follow the rules and round, and then you'll get the right answer. It's really in lab where this comes up, where you do a lot of sequential calculations and you have to go from A to B to C to D to E. You don't necessarily want to round off A and then B and then C and then D. By the time you get to E, you've created a lot of rounding errors. This is how you shoot a rocket at Mars and miss it. So you keep an extra couple digits, round at the end, and when you shoot a rocket at Mars, it goes to where you expect. Okay, so that's a quick sig fig problem. We'll see another sig fig problem or two this week. We'll try to do one each day just to help us prepare. I just know sig fig sometimes is a tricky problem, and I want to make sure we have that hopefully down pat. Okay, let's talk about the atomic mass unit scale a little bit more to try to figure out, like how it is that this works, and then how we can use it to quantify things like atomic weights of elements. We'll soon see that the periodic table also tells us average atomic weight. Like carbon says 12.011, oxygen 15.9994, that we're seeing listed on the periodic table the average atomic weights for those elements. And so the scale given for those atomic weights is usually thought of as being the atomic mass unit scale. We'll talk about grams per mole or molar masses in our next chapter. They could also correspond to that too. The atomic mass unit scale is that one we were alluding to previously, that one carbon-12 atom was defined to be 12 AMU exactly. And so that was historically how the AMU scale was defined. I'm not going to talk about how it's technically been changed lately over the last 5 years or so. They've slightly defined the way we define masses from the IUPAC, the International Union of Pure and Applied Chemists, have slightly changed the definition of things. But I'm going to keep this idea intact that historically the mass of a single carbon-12 atom has defined the number of AMUs. And then another thing that you can define, or you can determine experimentally, actually, this value is the mass of a collection of atoms. And so if you were to take 6.02214.076 times 10 to the 23 carbon-12 atoms, which is a big number, so that's Avogadro's number. So if you take an Avogadro's number of carbon atoms, that they have a mass of 12.000000, and I think 2 more 0 grams, like that precise amount of mass. And so you then go into the lab and say, well, what's the precise count of atoms to some placeholders? Because you're doing this experimentally, you then become limited by how well you can determine these quantities. And it's to about 10 digits of precision that this has been defined or carried out in a lab, and it's equal to precisely 12 grams. And so it's there that you kind of can come up with this link between the AMU scale and the mass scale, grams and the mass scale of AMU. So you can then say, well, what's the mass of one carbon atom in grams? I don't think I'm going to do this math here, but I think we'll just try to close off with this thought example here, that you can kind of connect how many grams there are in one single carbon-12 atom, and then you can connect that mass to be equal to 12 AMU, and that gives you a conversion factor between AMU and grams. I'll give you the end conversion here, that if you were to take 1 gram and then define what it is in terms of AMUs by just looking at one carbon-12 atom, defining the carbon atom's mass, but in grams, it's going to be really small. It's going to be like 10 to the minus 24 grams. It's going to set that conversion between grams and AMU, that 1 gram is equal, therefore, to 6.022140076 times 10 to the 23 AMU. So in other words, the AMU is really small. So if we do this conversion the other way, if we say, well, what's 1 AMU in grams? That's just dividing both sides by Avogadro's number. So if I take 1, divide by 6.022140076 e to the 23, that gives me 1.6605. I'll just dot it. But times 10 to the minus 24 grams. So an AMU is really small. Very, very small amount of mass. Atom's very small too. I just remember this other thought example I did last semester. I was putting this into my head of like, if you could take a carbon atom, a mole of carbon atoms, a mole of carbon would weigh about 12 grams. So 12 grams of carbon, not very much carbon. That would be like a third, or that would be probably about the mass of like a sugar packet. Okay? So if you took a mole of carbon and you just took the atoms end on end, and just took one carbon atom, the other carbon atom, the other carbon atom, the other carbon atom, and you went to the sun and then back, like how many times could you do that with that 12 grams of carbon? You can actually go to the sun and back about over 1 trillion times with a single mole of carbon. So the atom's very, very small, and there's so many of them that you can align them end on end in a single row back and forth from the sun over 1 trillion times. That just, the atom's very small. There's a lot of them in a sample. It's very hard to imagine the degree of small that the atoms are. If you also look at the magnitude of Avogadro's number, 10 to the 23, that's multiple orders of magnitude more currency than we have on Earth. So like if you look at how much monetary currency we have, I think it's in the 10 to the 14 to the 10 to the 15 range. But if somehow you could have 10 to the 23 nickels, if you could take an Avogadro's number of nickels and lay them end on end across the equator, you could circle the Earth over 1 billion times. So I mean, it's really pretty amazing how small the atom is. Okay, so anyways, getting back to average atomic weights of an element. So an element's average atomic weight is going to be the sort of weighted average of all the naturally occurring isotopes. And so the average atomic weight, we can do this as a summation sign. Whenever you start doing like weighted averages, usually is where you invoke like a summation sign, and you say the average atomic weight of a given element is the sum over the fraction of all isotopes that exist naturally times the atomic weights of those isotopes that are naturally occurring. And we can do a couple examples with this. The easiest example is an element like iodine that only has one isotope. So if there's a given element that naturally exists with just a single isotope, one of those examples is iodine. It's 127 is its most stable isotope. Iodine's element number 53. So that given isotope would have 53 protons for 74 neutrons. And so this is 100% of a sample of iodine is this one isotope. So it has a fraction of 1. So its atomic weight would just be its listed atomic weight in the periodic table. So 126.90447. We just get that right from the periodic table. Now, I wouldn't expect you to remember this, but it just turns out some elements only exist as one isotope, and in which case you can look at the periodic table and determine that isotopic mass for that particular isotope. And now, how could you determine iodine was 127? Now, this is where, let me backtrack a second to talk about the mass of the proton and the neutron. That you can't just sum up, like if you go back to carbon-12, for example, 6 protons, 6 neutrons. Some of you guys may have already been thinking about this, that if you sum up the mass of 6 protons and 6 neutrons, you don't get 12 exactly. Did anybody have that thought? Was anybody thinking that how do you get a 12 AMU mass of an atom when the subatomic particle masses sum up to a mass that's greater? Well, that difference in mass between the sum of all the subatomic particles that an element contains or an atom contains, the difference between that mass and the actual mass of the atom is the stability of the nucleus. So that relates to the nuclear stability that those subatomic particles have in the nucleus. And those masses that we listed, if you remember the 1.0087, the 1.0073 AMUs for the proton and neutron, those are resting masses. And those particles are not resting when they're in the nucleus. And so the nucleus is going to have a different mass than the sum of its constituent subatomic particles. So in other words, if you want to determine the mass of iodine-127, you can't just sum up 74 neutrons, 53 protons. It doesn't work that way. But the way it does work is that whatever the actual mass of that nucleus is, since there's only one, is the mass that's listed on the periodic table. Now let's talk about carbon for a minute. Carbon, we mentioned, was about 99% carbon-12. Precisely, it's about 98.93% carbon-12, which is exactly 12 AMUs by definition. And then carbon-13 is 1.07%, a little over 13 AMUs. And then carbon-14 is just such a small trace that it's not going to factor into the average atomic weight equation for carbon, so small and its abundance. So can we calculate for carbon its average atomic weight? So the average atomic weight of carbon should just be the sum of the fraction of each isotope. Now fractions, we just go by the percentage without the times 100%. So the fraction of carbon-12 would be 0.9893. So the difference between a fraction and a percent is just multiplying by that 100%. So we just take this number as its fraction times the atomic weight of carbon. I'm going to write in that exact again because it's 12 exact AMU. And then we're going to plus the 0.0107 times 13.0034 AMU. Let's think about sig figs here too. Why not? It seems like a good sig fig problem. How many sig figs should 12 times 0.9893 have? Should it have 2 or 4? If you think 2, it's because we're not thinking what the word exact means. So the exact in 12 means that that's 12 with like an infinite number of zeros after it. So 12 has like it's a perfect number. It's an exact number. So we're not going to round to 2. We're going to keep all 4 that we start with. So kind of a trick question, but this is also like conversion factor-ish. So like we don't round like 100 centimeters in 1 meter. If we're converting centimeters to meters, we don't round that to 1 sig fig because it's a perfect conversion. Same thing here. We're not going to round to 2 sig figs because the 12 AMU was an exact number. I could have written an infinite number of zeros and you'd say, okay, we'll keep 4 sig figs then. So I get 11.8716. And the 4th sig fig, I'll indicate here, that's the last number that's significant in the quantity. And again, we could round or we could keep it. Let's keep it for now. And then the next numbers are just ordinary numbers. So 0.0107, 3 sig figs times a bunch of sig figs. So the second multiplication step is 0.13913. And so that should be good to the 3rd sig fig. So now just 3 sig figs times 6 sig figs, we round to 3, or would report the value to 3 sig figs. And so when we do our subtraction step, we're going to round this result here to the hundredths placeholder. So I get 12.0107, which is rounding to this placeholder. Now, if you then inspect, so we would report this from this math here to be 12.01 AMU as the average atomic weight of carbon. I wish we didn't have to think sig figs with every problem, but I think it's good since we have a test on it coming up that we try to apply the sig fig rules. Now, how do we get a periodic table here that says 12.011? Or if you look on some other periodic tables, it can be even more precise. To get a more precise atomic weight, or to know that it's more precise, we would just have to have slightly more precise atomic weights and fractions. So if we use more precise data, we could get a slightly more precise atomic weight to come out with confidence that that's the proper atomic weight. Okay, so let's talk a little bit about the periodic table in terms of some of the different groups that are important and a few details that are worth pointing out. So we know, I think, that the periodic tables, by increasing atomic weight and by increasing atomic number, and so by atomic number going up in that order, but then also grouping elements into sort of columns that then have some properties in common with each other. And so hydrogen, helium, both gases. Then we get to lithium, which is a metal. So we restart our for the second row of the periodic table across lithium. So we have a group of elements here that we call the alkali metals. Now, it's such a similar name to the next group of metals. The next group of metals just here, the second group, these are the alkaline. So you have the alkali and the alkaline, or the alkali or the alkaline, however you want to pronounce those words. But two groups of elements that sound similar, but they're different groups. So the first group, the alkali, the lithium, sodium, potassium, these form +1 cations, and they're most commonly found form in nature. And then the alkaline form +2 cations. Now, if we jump across to the noble gases, maybe we can pick out why those are forming +1 and +2s are, and we've already talked about these a little bit, but the noble gases are the group of elements that are stable as monoatomic gases. So the noble gas group are stable as single atoms without needing to exchange or go to cations or anions. So they have the most stable configuration and count of electrons that are possible within their nuclei. So they have, in the electrons that they can counterbalance, so they have the right balance of electrons and charge, that they're stable as is. And then we can use that as kind of a thought of, oh, well, lithium's just trying to lose an electron to come up with that noble gas configuration of electrons. So if lithium loses an electron, it has 2 electrons just like helium does. If potassium loses an electron, goes to 18 electrons, it then has the same number of electrons as that noble gas argon. So it's just a way that elements gain some stability or form something that then allows them to interact with something else that allows their stability to be higher than if they just existed as their monoatomic atoms. And so calcium's 2 away, so calcium has 20 electrons. If it loses 2, it goes to 18. So obtaining a noble gas count of electrons is how a lot of elements obtain some stability. Aluminum forms a +3 ion as a stable ion. So aluminum is really common to form a +3. Technically boron can too, it doesn't always do it, but aluminum is probably the best example of an element in what we call the main group. The main group elements are let me go laser pointer here. So the main group elements are the sort of boron, carbon, nitrogen, oxygen, the sort of this group of elements, and then the alkali and alkaline are what we generally call the main group elements. Transition metals are in the middle. So all these elements here are the transition metals. Now, transition metals will form a variety of charge states. So we can't just look at every element on the periodic table and define the charge that its most stable cation would contain. So when we get to an element like, let's say, titanium or vanadium or chromium, that we're going to have to tell you what the charge is for that atom. We'll come up with a Roman numeral charge system. So we'll come up with a system that'll say titanium 2 will be titanium with a +2 charge. We'll talk about that later with nomenclature. So I just want to introduce now that all these elements in the middle will have a variety of different charge states that are possible. So we're going to have to tell you or come up with a nomenclature system to understand what their charges are. A couple other groups of elements worth naming here would be the halogens, or the fluorine, chlorine, bromine, iodine group. The oxygen group is worth pointing out. The halogens form -1 ions because they're 1 away from that noble gas count if they pick up 1 electron. The oxygen group tends to form -2 ions, and then the nitrogen group tends to form -3 ions. But also, these non-metallic elements will tend to form the molecular bonds with other non-metallic elements. So what you're going to find is a halogen, like chlorine, will form an ion with sodium, but it will share its electron with something like hydrogen or another chlorine atom. So in terms of metallic versus covalent bonding, we tend to see that molecular or covalent bonding between non-metallic elements. So the non-metallic elements are things like hydrogen and then all these elements over here. So those are our nonmetals. When they bond with each other, they tend to go covalent, shared electrons. And then the metal-nonmetal pairs tend to go ionic. So this is just kind of summarizing some of the key elements. I didn't name the oxygen group, but you could call those the chalcogens, is the oxygen group of elements. So oxygen, sulfur, selenium. You won't see too many examples at the very bottom of these groups. Like if you look at the halogens, I don't think you're going to see any examples that use astatine because it's such a rarely found element. But you'll see a lot of examples of fluorine, chlorine, bromine, and iodine. So those are halogens or noble gases, the stable group of elements. So these groups are worth knowing by name. And just then some of their key properties, the +1s, the +2 ions, the -2s, the -1s, and then the neutral, as their most stably found or most commonly found charge state in nature. Now, how we determine things like, you may be wondering for like the carbon-12 example, how do we determine abundance and atomic weight? We do that with an experiment called a mass spectrometer. I won't define this too much. I just want to introduce that there's an instrument that can be used to determine both the abundance, like how much of the chlorine-35 versus the 37 there is. Like if you integrate the area under the curve here for these atoms, it turns out to be about a 3-to-1 ratio of chlorine-35 to 31. So about 75% of a natural sample is chlorine-35, and about 25% of a natural sample of chlorine is chlorine-37. The atomic weight of chlorine-35 will be close to 35 AMU, because if you think you have 35 summed up protons and neutrons, which are about 1 AMU each, so you're going to find that that mass is pretty close to, not dead on, but pretty close to 35 AMU, as opposed to like 35 and a half or 34 and a half and 35 and a half. So pretty close to 35 AMU, pretty close to 37 AMU in that mass. If you go back to the iodine 127, pretty close to the mass of 127, it's like 126.9. So you'll find that a given isotope has a mass pretty close to its number of subatomic particles. And then from the ratio, can we predict what we expect the atomic weight of chlorine to be? So if you're more abundant in the 35, less abundant in the 37, do we see how the average atomic weight of chlorine is going to be closer to 35? Let's think of another thought. If it were 50-50, if the natural abundance of 35 and 37 were 50% each, do you see how the average would be 36? So if we had more 37, the average would be closer to 37. More 35, the average closer to 35. So we'd predict the average to be right about here. So about 35.5 AMU would be our predicted atomic weight of chlorine. If we look in the periodic table, it's 35.4527. So 35.45. So you can sort of predict for some elements if you know something about the element in terms of the average atomic weight. Like bromine is another good example, where bromine has two stable isotopes. It's maybe hard to see the scale here, but it turns out one of them is 79 bromine, the other one is 81 bromine, and they're about 50-50. So what do you expect the atomic weight of bromine to be? About the average of the two, so you'd expect it to be pretty close to 80 AMU, so bromine's atomic weight, 79.9. So right around the simple average of the two isotopic masses of those two isotopes. If you know, like carbon was almost like 99% 12, tiny fraction carbon-13, so the mass of carbon-12 on average, just a smidge over 12, 12.01. So you can get a sense of how abundant, if you know that an element has like two isotopes that are mostly part of its natural occurring isotopes, if it's 99% that one isotope, it's gonna be pretty close in terms of the average atomic weight to that one isotope. This is looking at two bromines put together. I won't talk too much here, but if you look at mass spectrum, you can see for Br2, a stable molecule of bromine, you can see kind of the impact of having both of them as 79. One is 79, one is 81. Both of them is 81. There's two ways to have the 79, 81, so that becomes more abundant. I don't want to talk too much about that here, but you can see some relative abundances of molecules and atoms within what we call a mass spectrum. So I just want us to see that the mass spectrum is how we're getting some of this data like mass percentages and abundances and atomic weights. Now, this is like just trying to show us that like if you have a formula like CH4, I'm seeing non-metallic elements, so it's going to be that shared bonding, not an ionic compound. And so we end up kind of like seeing these molecular bonds. We'll talk more about those in chapter 8. And so for a molecule, what we want to know is the molecular formula. The empirical formula is something that we can write, but it doesn't mean a whole lot. Like CH4, molecular and empirical formula is just CH4. But if I had like ethane, C2H6, you might say, well, the empirical formula for that would be CH3, but there's no real meaning in compounds that share an empirical formula. But you can simplify formula and write what the empirical formula is. That'll relate to later chapters, us determining an empirical formula and then later determining a molecular formula. So we'll come back in later chapters that for molecules, we usually want to know their molecular formulas. That's what makes a molecule special. That's its collection of atoms in a single molecule of that compound. So that's what we're going to want to know, is how to kind of write the formula for a single molecule. Now, I'm going to skip over a couple slides that we'll get into next time and just head to our attendance quiz for today. So we'll just wrap class up with tracking your attendance for today. This won't always be at the end, but might be at the start, middle of class. But we'll just wrap up with this here today. So just get that attendance in for today, and we're good to go. And I'll see you guys back here on Wednesday.